This is section 4.3 on polynomial division. If you think about the things that we've done so far, we certainly know how to add and subtract polynomials. That's just a matter of combining like terms. And we've definitely talked about multiplication of polynomials when we talked about expanding. But what we haven't yet talked about is how to divide polynomials. So that's the content here in section 4.3. And in order to do this, and this is something that we'll be using actually in the next section or two coming up, in order to do this, we need to first of all talk about the division rules for exponents, and then we can expand that into dividing full polynomials. So, if I look at my division rules for exponents, we'll start here with x to the a divided by x to the b equals x to the a minus b, or in other words, to divide our power functions, we just subtract the exponents. If you think about that for a moment, if I wanted to take x to the fifth and divide it by x to the third, if I were to actually write that out, x to the fifth divided by x to the third, notice that we would be able to reduce our fraction several times, right? X divided by x is 1, x divided by x is 1, and x divided by x is 1. So we just end up with 1 times x, or x squared. And you can see that that subtraction of the exponents definitely works out. In a couple of quick examples for us, if I wanted x to the 8th divided by x squared, I would just subtract the exponents and get x to the 6th. In this next example, I have to worry about both the coefficients as well as the powers of x. So with my coefficients, 16 divided by 24, I could divide 8 out of both of those, so I'll reduce that to 2/3. And then I'm going to subtract my exponents to get x to the 7th. By the way, it's also possible to write this as a traditional coefficient, like 2/3 multiplied by x to the 7th. Both of those mean the exact same thing. All right, my second rule. If I have a fraction or a quotient, all in parentheses raised to the nth power, I can apply that exponent to both the numerator and denominator. So to raise a quotient to a power, apply the power to both numerator and denominator. Again, a quick example to kind of show you how this works. If I had something like x over y squared, what that really means is multiply x over y by itself. But when I multiply the numerators, x times x is x squared, and when I multiply the denominators, y times y is y squared. So the ultimate effect is I did just end up squaring both top and bottom. If I think of that in my couple of examples over here, I want to take the third power of this fraction, so that would be 5 to the third divided by d to the third. Now, of course, the numerical part we can do. 5 to the third is 125 divided by d to the third. And that would be our simplified form. How about this next one? Fraction raised to the 4th power means I raise the numerator to the 4th power. And here's one of the rules we saw before, right? Raising a power to a power, you multiply the exponents. So n to the 20th divided by 2 to the 4th would be n to the 20th divided by 16. This is another one that can be written another way. If you think about the fact that the coefficient in the numerator is really 1, if I wanted to, I could write this as 1/16 n to the 20th. And then it looks a little more traditionally like a coefficient times the power of my variable. But again, they mean the exact same thing. All right, my last note here is don't forget the unrule. Don't forget that if you have a sum or a difference raised to a power, it is not possible to simply apply the power to each term. So I can't just say x to the n plus y to the n, or x to the n minus y to the n, right? Instead, these require multiplying binomials. Right? Many of us think of that as the FOIL method. All right, so let's look at this example. My square on the outside of this whole fraction does mean that I can apply the power to both the top and bottom, but I do need to be a little careful. When I apply the power to the top, I'm just going to write it as x plus 8 squared, and I'll go ahead and write the bottom as 3x squared. Now on top, because it's a sum, I can't just square the term separately. I really have to multiply out x plus 8 times x plus 8. On the bottom, you can either write out 3x times 3x, or because this is a product, it is okay to say square each factor separately, right? And that's a big difference between the top and bottom. When you're adding or subtracting, it's like multiplying binomials. We're going to have to multiply it out. When you're multiplying, right, 3 times x, it's okay to apply the square to each factor separately. All right, let's finish this one up. In the numerator, I'm going to get x squared. My outers and inners are both plus 8x. So I'll end up with a plus 16x plus 64 divided by 9x squared. All right, so there's a little bit about dividing binomials. In this section, we'll primarily be making use of this top version, where we're simply saying that to divide, we subtract exponents, but I wanted to give you the other pieces of the division at the same time. All right, so let's now say that instead of just a monomial divided by a monomial, we'd like to take a higher degreed polynomial and divide it by a lower degreed polynomial. And the first thing I'm going to say is we can rewrite that as a long division problem. The lower degreed polynomial divided into the higher degreed polynomial. We're going to actually learn how to do this 2 ways. The long division way, which we'll do first, works for all polynomial division problems, and that's why it's important to know. But there's a little shortcut called synthetic division. This one only works when the divisor is the form x plus a or x minus a. So it's a bit limited in its scope, but it's going to turn out that that's what we're going to need a lot in this class, so it's a worthwhile shortcut to learn. All right, but we're going to start here with the long division. This works all the time. So I'm going to take my divisor, my x plus 5, and divide it into x cubed plus 3x squared minus 6x plus 20. When you divide, you always want to start by concentrating on just the first terms. So what I want you to think about is the x cubed divided by the x, right? Subtracting the exponents, 3 minus 1, would give me x squared. And that's the first piece of my quotient. Now you might notice that I'm lining up my like terms here. I put the x squared over the other x squared terms. It's a good habit to get into. All right, I'm now going to take that x squared and I'm going to multiply it by the x plus 5. So that's going to give me x to the third plus 5x squared. And then finally I subtract. So subtract those terms, subtract those terms. X cubed minus x cubed is just 0. 3x squared minus 5x squared would give me negative 2x squared. Now that's one complete division cycle. I'm going to keep repeating that cycle. Divide, multiply, and subtract over and over again until I get to the end of my problem. So let me just bring down the rest of this so we can kind of start over. That's what I've still got. And I'm going to go back now to the division step. So I'm taking my negative 2x squared, dividing by x to the first. I'll get negative 2, subtract the exponents, x to the first. I'm going to take that negative 2x and multiply by the x plus 5, which is going to give me negative 2x squared minus 10x. Now I'm subtracting, and keep in mind subtracting a negative actually means that it turns into a positive, right? So my positive and negative 2x squared terms, those add up to 0, and those are going to add up to a positive 4x. And there's a complete second cycle of the division process. All right, I'm going to bring down that plus 20, and it looks like I got one more cycle probably left to go. Start with division. Take that 4x, divide it by the x. You're just going to get a positive 4. So plus 4 here. Take that 4, multiply by the x plus 5. That gives me 4x plus 20. And this time when I subtract, I end up with 0. So that just means that the division came out evenly and there was a 0 remainder. We'll talk more about other remainders later, but this first one has no remainder. So there's the division process, which we'll go through another time or two. But what I want to focus on next is actually, what does this tell me? The fact that the division came out evenly now tells me that if I multiplied the x plus 5 and then this quotient, x squared minus 2x plus 4 together, that would give me the original polynomial. Or in other words, I now know that that polynomial has a factored form, x plus 5 times x squared minus 2x plus 4. That's actually a big advantage of this polynomial division, because if you notice, if I had looked at this four-term polynomial rather, I would not have been able to factor this before that division. With 4 terms, I might have tried grouping, right? But you can see pretty quickly it wouldn't work. I'd factor an x squared out here, giving me x plus 3. And I could factor a negative 2 out there, which is not going to be x plus 3. So could we have factored this using a normal factoring technique? No. Again, if we tried grouping, Taking out the x squared gave us x plus 3. Taking out a negative 2 would make that 3x, minus 10. And since those don't match, grouping didn't work. So this long division potentially gives us a way of getting a factored form where we couldn't have using our other techniques. Okay? Now, that worked out great because the remainder just happened to be 0. That's not always going to be the case, but when it is, we know a new factored form. All right, let's try another division. I've got 2x minus 1 divided into this cubic polynomial. And I'm going to try and do this one without writing out quite as many of the side things. If you get lost, by all means go back to the other one, take another look, and you could write those side things out for yourself. But I just want you to kind of see what you're kind of aiming for as we go here. So I start with the division. 6 divided by 2 would be 3, and x to the third divided by x to the first is going to be x squared. So 3x squared. I'm going to go ahead and do my multiplication, but rather than writing it off to the side, I'm just going to see if I can kind of do a little bit more work mentally this time. So 3x squared times 2x, 6x to the third, and 3x squared times negative 1 is negative 3x squared. I do need to subtract, which makes that negative and that positive. And so I'm going to end up with the 14x squared. And I'll bring down the rest. Let's divide again. 14 divided by 2 is going to be 7. And when I subtract the exponents, x to the first. So plus 7x. Multiplication step. 7x times 2x, 14x squared. 7x times negative 1 is negative 7x. Subtract makes that negative, but we'll make that positive. So I have negative 10x. And I'll bring down that plus 8. All right, dividing again. Negative 10 divided by 2 would be negative 5, and the x's just divide out, so minus 5 gives me a negative 10x and a plus 5. When I multiply, subtracting makes that one positive and that one negative, so I end up with 3. I know I'm done dividing, both because I've kind of finished off with my constant term here, but also the degree here is now 0, which is smaller than the degree of the divisor. So I'm finished. This time I do have a remainder, a non-zero remainder. Okay. So how can I write this? Well, one thing we can do is just literally write the answer as a quotient with a remainder. So I can just say it's 3x squared plus 7x minus 5 with a remainder of 3. But if I, for some reason, need to use that answer mathematically, that remainder kind of gets in the way. So what I can do instead is I can write the remainder as a fractional term of the quotient. So I still have my same quotient, 3x squared plus 7x minus 5, plus, I'm now going to make a fractional term out of the remainder. The remainder was 3, And that 3 has not yet been divided by the 2x minus 1. So basically I'm saying, yeah, I still got 3 that would have to still be divided by whatever the 2x minus 1 is. And that makes my remainder into a fractional term. And altogether, that could be my answer. The disappointment of having a remainder is that 2x minus 1 then is not a factor of our original cubic polynomial. So I don't have a factored form of this that I kind of got from that answer. All right, I want to do one more long division because so far we've only been dividing by linear divisors. So let's do one where we have to divide by a quadratic divisor. And that doesn't look very focused. There, that's better. So here's my division problem. My divisor is x squared minus 2x plus 2. And when I go to divide, it's noted here, but notice that it's kind of like there's a missing term. There's no x cubeds there. It's really important when you divide that all of the powers be represented. So when I write down my divisor, I'm just going to write that I have 0 x cubes. And then all of the rest of the powers in descending order are there, so I can just finish. But that 0x cubed as sort of that placeholder is important anytime you have a power that's kind of missing. All right, so let's go ahead. X to the 4th divided by x squared would be, remember, subtract exponents, x squared. We're going to multiply x to the 4th minus 2x to the 3rd. And now you can really see why I needed that 0x cubed to keep my like terms lined up, plus 2x squared. All right, I'm subtracting, so minus, plus, minus. And I get 2x cubed plus 3x squared, and then I'll bring down the 4x and the 9 as well. All right, let's keep going. Again, when you divide, you only concentrate on the first terms. So 2x to the 3rd divided by x squared is going to be 2x to the 1st. That's positive, so plus 2x to the 1st. Multiplying gives me 2x cubed minus 4x squared plus 4x. Subtracting is negative, positive, negative. So I have 7x squared. Now this would be a missing term. The 4x minus 4x is 0x. So I'm going to be sure I write it down, plus 0x. I don't want to lose that spot. Plus 9. All right, dividing again. 7x squared divided by x squared would just be a plus 7. And when I multiply, I get 7x squared minus 14x plus 14. Subtract plus minus, and I've got 14x minus 5. All right, that is my remainder. I know that I'm done dividing because, again, the power here, the first power, is now smaller than the power of my divisor. And so I know I can't divide anymore. So I have a quotient and I have a remainder. Okay. Let's write this answer with the quotient and remainder and then also using that fractional form. So the division quotient was x squared plus 2x plus 7, with a remainder of 14x minus 5. But algebraically, I would probably want to write that as x squared plus 2x plus 7 plus 14x minus 5 over x squared minus 2x plus 2. All right, that's your long division process. I know it takes a bit of time to run through and a little bit of practice, but it's fairly repetitive, and sometimes that's a good thing because repetitive things, once you get the pattern, it's not so bad. All right, I also wanted to mention synthetic division. And again, you have to learn long division because that's the one that works all the time. Synthetic division is a shortcut. But again, it's a shortcut only in one specific case. It only works if you're dividing by either x plus some constant a or x minus some constant a. Okay? Only works in that special case, but it's going to turn out that that case is especially important to us, so it's worth taking the time to take a look. Okay? All right, if you look back at our 3 examples that we've already done, only one of them falls into that special case. Okay? The most recent one we did has an x squared on the bottom, so that definitely doesn't work. The example before that, we were dividing by 2x minus 1, and the special case, it has to just be a 1x, so that one didn't work. But our very first example, our divisor was x plus 5, and that is the one of the special forms that does actually work with the shortcut. So I'm actually going to redo this example. We already know what the answer is, right? I'm going to redo this example using the synthetic division shortcut. Here's what it looks like. We take what we're dividing by, and again, it has to start with just a 1x. Whatever the value is here, in this case plus 5, you take the opposite. So I'm going to take minus 5. And then as far as the numerator is concerned, rather than writing out that whole polynomial, I'm just going to write out the coefficients. The 1, 3, -6, and 20. Here's how the synthetic division process works. I start by just taking this first one and bringing it down below my line. And then from here, it's going to be multiply and add over and over again. So multiply, -5, add, -2. Multiply, +10, add 4. Multiply, -20, add 0. So what's my answer? Take a look at the answer that we got when we did the long division. Can you see what the answer I got with synthetic division really means? The 0, the remainder, is represented here. And the 1, the -2, and the 4 are the coefficients in my quotient. So when you use synthetic division, the last value is always your remainder. And you can kind of work backwards. 4 is the constant term. -2 would be the linear term, x to the first. And then +1x squared would be the quadratic term. They always go in order, so it's okay if you work backwards. Once again, because we got a remainder of 0, it would then be possible to say, yes, there is a factored form to this cubic polynomial, and it is x plus 5 times x squared minus 2x plus 4. Okay. So the result is still the same. All right, I would like to go ahead and just try a couple of other examples with the synthetic division process. When it comes out with no remainder, we'll write our factored form. In other cases, we'll know that it didn't help us to find a factored form. First of all, let's verify that this is the special case where synthetic division works. I just have 1x, and either plus or minus, in this case, a number. So this is the synthetic division will work case. I take that number, the opposite sign, so positive 1/3, and then my coefficients. 6, -5, -2, 1. All right, I start by just bringing down the first number, the 6. And then I'm going to begin the multiply and add. Multiply, 6 times 1/3 is 2, and add, -3. Multiply, -3 times 1/3 is -1, and add, -3. Multiply again, -3 times 1/3, so -1 again, and add, giving us that remainder of 0 again. All right, let's write down the quotient. -3 would be the constant term, and then I'd have -3x to the first, and 6x squared. And if this was longer, of course, then I'd just have x cubes and x to the fourths and so on. But in this case, my quotient came out evenly, no remainder, and that's it. That's the result of the division. So it says use this result, since there was no remainder, to write our original polynomial in factored form. So I would have x minus 1/3 times all of this. Now, if you're looking at that and thinking, well, that looks a little weird to me because when we were factoring, we never used fractions. That's actually true. If you wanted this to look more like kind of the normal factored form that you're used to, notice that this quotient actually has a GCF. You could factor a 3 out of this, right? So let's do that. We have x minus 1/3. Factoring out a 3 would give me 2x squared minus x minus 1. Now take that GCF that you just factored out, and instead of multiplying it into the second part, multiply it into the first part instead. Makes that 3x minus 1 times 2x squared minus x minus 1. So that's a little bit more normal looking, where we don't have any fractions in our factored form. All right, I got one more synthetic division problem for us. In example 6 here. And the first thing I'm going to notice is, yes, I can use synthetic division. It's just 1x plus or minus something. So let's see, it's a minus 4 here. That means I'm going to use a positive 4 in my division. And I have to be a bit careful here. There's terms that are sort of quote-unquote missing, right? I'm going to notice there would have to be a 0x cubed here, and actually a plus 0 at the end because there is no constant term either. So when I put all of my pieces in, it's going to look like 1, 0, negative 10, negative 22, 0. Okay? Those zeros are really important, or it's not going to work out correctly. All right, I'm going to bring down the 1, and then I start. Multiplying gives me 4, and that adds up to 4. Multiplying here is 16. That adds up to 6. Multiply to 24 adds up to 2. Multiplies to 8 adds up to 8. Remember, the last one is always the remainder. So this time I am going to have a remainder of 8. And then I'm going to work backwards. 2 is my constant term. 6x to the first plus 4x squared plus 1x cubed. Or, since it did not come out evenly, I don't have a factored form, but I could write my solution instead of with the remainder. I could write the remainder in a fraction form, just by writing x cubed plus 4x squared plus 6x plus 2 plus 8 over the original divisor, x minus 4. All right, so there's your polynomial division.